Hello and welcome back. Today we will have lecture 2-1 on probabilistic robotics. Our learning objectives are to provide an introduction to uncertainty in probabilistic robotics, give an overview of the axiom of probability theory, describe the difference between joint and conditional probabilities, define discrete and continuous random variables, and demonstrate a marginalization example. As this entire course is built upon some work done by Wolfram Borgard, Deirdre Fox, and Sebastian Thrun as part of their Probabilistic Robotics textbook, Intelligent Robotics and Autonomous Agents, as well as the course, and you can Google to learn more about their work. So there are several challenges in the study of mobile robotics, including there's some physical, mechanical, and electrical issues, such as sensors are prone to errors and may have bad readings. Sensors have limited range and resolution. They are also subject to noise as well as braking. Actuators are going to drain batteries and may not be small or powerful enough for the mobile robot. And actuators can also be unpredictable because of noise, wear and tear, mechanical failure, etc. In addition, you can also have some challenges with knowledge representation and retrieval, such as how to represent the real world in a robot's limited memory, how to extract relevant information from large amounts of sensor data, which is called our perception, and how does the robot adapt to a dynamically changing and unpredictable environment. So because of all of these challenges, there's an enormous amount of uncertainty in a robot's environment, as well as the robot's state, its location in the world, as well as the status of the world. So the robot's internal model of the world or environment is typically going to be approximate because of these challenges. And also, in order to have the robot make decisions in real time, you have to use these approximations so that the robot can keep moving. So the robot acts upon the environment using this insufficient information from the sensors as well as this inaccurate internal model. And so the robot can never make decisions with complete certainty. And this is where probability comes in. So probabilistic robotics means the robot suffers from some uncertainty due to its sensor uncertainty as well as its motion uncertainty. For example, the robot senses a round object, an orange round object. The robot asks, is that really a ball? My sensors say it's orange and round, but is it a ball? Or if we're talking about motion, the robot has commands to get home, but then it has to use odometry error to estimate, am I really home or not? So this is where probabilistic robotics comes in. So it means it's necessary to use probabilities to model this uncertainty and to represent ambiguity and degree of belief in a mathematically sound way. So the key idea here is to have an explicit representation of uncertainty. We use the calculus of probability theory. So from the perception, we get a state estimation, and from the robot's actions, we get a utility optimization. So the axioms of probability theory states that the probability of A denotes that A condition A is true. So a probability must be between 0 and 1. So we say that the P of A is between 0 and 1. If the condition is true, then the probability is 1. So we would say the probability of A is equal to 1. If the condition is false, then the probability is 0, or P of A is equal to 0. So if the robot detects an object in its world and it's like, is that an apple or a banana? This may not be enough for it to make that decision. It may need to have some sensor data. It may need to have a color sensor. Is this object red? Is this object yellow? Does this object look more oblong? Does this object look more like a circle? But with just the information we have, can it have the probability that it's a piece of fruit? Maybe. Or is the probability if it's an apple or banana? We may not have enough information yet to be able to make those decisions. So the probability of A or B states that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And we can see that here in this Venn diagram, because if we have these overlapping probabilities, then you know that the probability of A and B will actually be included twice. This is why you have to subtract off the probability of A and B. So we would say that the probability of an apple or the probability of a banana is the sum of those two minus the probability of an apple and banana, as shown here. And then anything outside of that Venn diagram would be the example of not the probability of A or B. So the derivation of the probability of not A is based upon what we learned on the previous slide. So the probability of A or not A would be the probability of A plus the probability of not A minus the probability of A and not A. So we know that the probability of A or not A is just the probability of a true statement, or 1. And that's equal to the probability of A plus the probability of not A minus the probability of false, because you cannot have A and not A. So then we would write that as 1 equals the probability of A plus the probability of not A minus 0. So finally we get something that hopefully we all knew from probability already, that the probability of not A is equal to 1 minus the probability of A. So now, discrete random variables. If we have X denoted as a random variable, and it can only take on a discrete number of values, then we can say that these countable number of values can be represented as lowercase x1, x2, and so on, xn. So the probability of the random variable X is equal to X sub I, or the probability of X sub I is the probability that the random variable X takes on a value lowercase x sub I. So we call the probability mass function. Or for example, the robot is in a home with 4 rooms. If each room has a different weight, the probabilities of all of those rooms must sum to 1. Then the probability of being in any room for the robot would be 0.7, 0.2, 0.08 plus 0.02, because we assume the robot cannot be anywhere other than one of those 4 rooms. It needs to add to 1. So the robot asks, what room should I go into? And I have weighted the probabilities of the lower rooms higher than the upper level, because we don't know how that little robot's going to get up those steps. Now, our continuous random variable, we say X can now take on any value along a continuum. And we call that the probability of the random variable equal to lowercase x, the probability density function. We normally will approximate this with the discrete case, knowing that we're typically going to use computers in order to calculate these values. So the question becomes, does X lie in a given interval? So is X contained between A and B? That would be the integral from A to B, P of X dx. When the robot moves around, this would be an example of a continuous variable as it moves around the environment. And the robot would then ask questions such as, I am in what location in the classroom? X comma Y, where that could take on a continuous number of values, assuming the robot can navigate most spaces in the room. What about joint and conditional probability? So joint probability states that the probability that the X is equal to lowercase x and Y is equal to lowercase y can be written as the probability of X comma Y. If X and Y are independent, which means that one does not depend on the other, for example, an example of dependent variable could be if my sensor sees an object, it could be a wall. But something that would not be dependent could be my sensor sees something red, it must be a ball. Those may not be dependent on each other because the ball does not necessarily have to be red. Although if my sensor sees something red, it must be an apple. That may be dependent because apples could be red, although we know you could also have green or yellow apples. So if X and Y are independent, then we say that the probability of X comma Y is the probability of X times the probability of Y. For a conditional probability, we say that the probability of X given Y is the probability of X and Y divided by the probability of Y, or that the probability of X and Y is equal to the probability of X given Y times the probability of Y. So that once again would be the probability that I am at a wall given that I sensed an object in front of me, or the probability that I sense an object and it must be a wall. And then once again, if X and Y are independent, then we can now write that the probability of X given Y is just the probability of X. As we see here, I see red and a round object. Is it an apple? Don't know. It could be a red soccer ball. So the law of total probability, as already stated, states that probabilities must sum to 1. So for the discrete case, the summation over all X would be P of X is equal to 1. For the continuous case, it would be the integral of P of X d of X is equal to 1. Or the summation of P of X over all X for the probability of X and Y. or P of x is equal to integral of P at x, y, dy for the continuous case. And the final case for conditional would be the probability of x is the summation over all y, the probability of x given y times the probability of y. Or in the continuous case, that would be the probability of x is equal to the integral, the probability of x given y, P of y, dy. So here's a marginalization example. So given the following table of probabilities, what is the probability that x is equal to a? So we have a column where x can either be a or b and a row where y can either be a or b. So the probability that x is a and y is a is 0.6. The probability that x is a and y is b is 0.2. The probability that x is b and y is a is 0.1. And the probability that x is b and y is b is 0.1. So if I want the probability that x is equal to a, that would be that first row. So the probability would be 0.6 plus 0.2 equals 0.8. What if I wanted the probability that y was equal to b? Then that would be that second column. So that would be 0.2 plus 0.1 equals 0.3. And notice here that the sum of all possible probabilities has to add to 1, which is 0.6 plus 0.2 plus 0.1 plus 0.1. And this concludes lecture 2-1 on our introduction to probabilistic robotics and marginalization. Have a robotastic day.